Assalamualaikum and hi everyone. Today, me and my friends will share with you information about electron microscope. Before we begin, I would like to take a moment to introduce our group members. We have Muhammad Aiman bin Rosli, Amni Huda binti Abdul Rasid, Muhammad Haikal bin Muhammad Zulkifli, Siti Nur Jamila binti Idris, and Elisa Adriana binti Abdul Syukur.
Okay, this is content about the presentation. First is introduction, second explanation, third detailed exploration, for example, 5 benefit and challenge, 6 future development and innovation, 7 conclusion.
Introduction of electron microscope. An electron microscope is a power scientific instrument that uses a beam of electron instead of light to create an image of a specimen. Because electrons have much shorter wavelength than visible light, electron microscope can reveal far more detail than traditional light microscope, having magnification of up to 10 million times of resolution at the nanometer or even atomic level. There are two main types of electron microscope. For the first one is transmission electron microscope. Transmission electron microscope is electron passed through an ultra-thin specimen revealing internal structure in great detail. Transmission electron microscope are widely used in material science, biology, and nanotechnology. For the second one is scanning electron microscope. Scanning electron microscope is electrons scan the surface of a specimen, producing detailed three-dimensional image of its surface topography. Scanning electron microscopes are commonly used in fields like forensic, manufacturing, and geology. Electron microscopes require a vacuum environment to operate and often involve complex sample preparation, especially for biological specimens. Despite their complexity and cost, they are indispensable tools in advanced research and industry for visualizing structures that are invisible to light microscope.
Electron microscopes are some of the most powerful imaging tools in modern science. Unlike light microscopes, which are limited by the wavelength of visible light, electron microscopes use a beam of high-energy electrons. Because electrons have a much shorter wavelength, this allows us to resolve structures down to the nanometer or even sub-nanometer scale, up to 100,000 times finer than what a traditional microscope can show. The basic structure of an electron microscope includes several key components. First, an electron gun generates a beam of electrons, often using a heated tungsten filament or a field emission source. This beam is then shaped and focused using a series of electromagnetic condenser and objective lenses. The sample is placed on a specimen stage within a high vacuum chamber, which is essential to prevent electron scattering by air molecules. Finally, detectors collect different types of signals, such as secondary electrons, backscattered electrons, or even X-rays, to produce image or elemental maps. The scanning electron microscope, or SEM, scans the surface of a specimen and detects secondary electrons to create detailed 3D-like surface image. The transmission electron microscope, or TEM, transmits electrons through an ultra-thin sample, providing image of an internal structures at extremely high resolution. A hybrid of both, the Scanning Transmission Electron Microscope, or STEM, allows for atomic resolution mapping of chemical elements. When electrons interact with a sample, they produce several types of signals. First, secondary electrons SE show surface topography. Second, backscatter electrons, or BSE, indicate contrast based on atomic number. And the last one, characteristic X-rays, analyzed using EDS, reveal elemental composition. In TEM, we can also analyze electron diffraction patterns and energy losses to determine crystalline structures and bonding. Modern electron microscopes can achieve resolutions below 0.1 nanometers, allowing us to see individual atoms. However, resolution depends on factors like accelerating voltage, lens aberrations, and sample thickness. That's why today's microscopes often include correctors, vibration isolation, and even cryogenic stage to improve clarity and reduce artifacts. Advanced software and AI now also assist in image reconstruction and data analysis. In summary, the electron microscope instrumentation is a complex integration of physics, engineering, and precision design. It allows scientists and engineers to explore materials at a level that's otherwise impossible, enabling discoveries in nanotechnology, biology, chemistry, and advanced manufacturing. Let's now explore a crucial real-world application, which is material failure analysis. When a critical component fails, like a turbine blade, a bridge joint, or a circuit, it's essential to know why. Electron microscopes play a key role by revealing the microscopic and even atomic level causes of such failures. SEM is commonly used to study fracture surfaces. For example, when analyzing a failed engine part, SEM can reveal features such as fatigue striations, which show repeated stress over time, crack initiation points, and grain boundary separations, which indicate how the fracture spread. These details tell engineers if the failure was due to material fatigue, overloading, pre-manufacturing, or corrosion. Allows us to go deeper inside the material. By slicing ultra-thin samples, the EM can detect dislocations and vacancies, precipitate particles in alloys, and grain boundary phases that weaken structural integrity. This essential is high-performance applications like aerospace metals, semiconductors, and nanomaterials. Failure analysis using electron microscopy typically follows this workflow. First, collect the failed sample. Second, use preparation tools like focused ion beam (FIB) to thin or section the sample. Third, image the sample with SEM and/or TEM. Fourth, interpret the structural or chemical evidence. And lastly, use these findings to fix the problem, whether that means changing the design or improving quality control or switching materials. This kind of analysis is used in aerospace to prevent fatigue failure in engines and wings, civil engineering to analyze bridge bolt corrosion, electronics to detect solder cracks and transistor failures, even in forensic science to determine if material defects contribute to accidents or malfunctions. In conclusion, the electron microscope isn't just a research tool, it's a detective instrument. By revealing the hidden causes of material failure, it helps protect public safety, extend product life, and guide innovation in design and manufacturing. It brings the invisible into focus and transforms microscopic evidence into actionable insight.
My name is Elisa Adriana and I'm going to talk about example of real-world implementation. First of all, in forensic science, scanning electron microscope is a powerful imaging technique increasingly utilized in forensic science for the comparisons of materials. By employing a focused electron beams, SEM allows analysts to view samples at incredibly high magnifications, revealing intricate surface characteristics that may indicate whether materials share a common origin. Invented in 1938, SEM can distinguish objects just 3 nanometers apart, far surpassing the capabilities of traditional light microscope. Involve an analysis to provide evidence for crime and law purpose. For example, an electron microscope may be used to analyze the acute details of a relevant specimen, such as residue from a gunshot or a sample of clothing fibers, blood, or other biological substance. The imaging process generates secondary and backscatter electrons, producing detailed images that help forensic scientists evaluate similarities and differences between known and unknown samples. Additionally, SEM can be combined with energy dispersive X-ray spectroscopy to provide elemental analysis, enhancing the accuracy of comparisons between seemingly identical materials such as different pieces of paper. These dual capabilities help forensic analysts determine the integrity and relationship between various forensic evidence, contributing to the overall investigative process. Next, in oil and gas industry, electron microscope is often used for industrial purposes to assist in developing new products and throughout the manufacturing process. For example, electronics industry use electron microscope for high-resolution imaging in the development and manufacturing process of semiconductors and other electronics. Other industries that may commonly use electron microscope as part of their production process include aeronautics, automotive, apparel, and pharmaceutical industries. By far most widely recognized application of electron microscope in Earth science related to petroleum industry and its byproduct, either, either petrochemicals or related synthetic materials. In such area, use of analytical electron microscope technique enable researchers to observe variation of molecular linkage that characterize families of synthetic products derived from petroleum. The results of such findings are critical in the search for new synthetic materials that are often much better suited to the specialized needs of modern industries and aerospace science than natural metal and their alloys. Many problems in petroleum technology involve a knowledge of the shape, size distribution, and degree of aggregation of particles of colloidal dimensions. The electron microscope has rightfully assumed an important position in research and analysis when the determination of particle statistics and surface structure is involved. With the aid of electron microscopes of extremely high resolving power, the size and shapes of molecules as small as 10,000 molecular weight calculated from centrifugation rates and light scattering data have been confirmed. The development of instruments of high resolving power and the improvement in specimen preparation methods have made observation of the atomic lattice and attainable world. Another example is used in natural resources. Electron microscope may be used to characterize and analyze organic materials, which is particularly valuable information for mining companies. The microscope can provide automated objective and quantitative information about the environment quickly. High-resolution scanning electron microscopes visualization of sedimentary organic matters is widely utilized in the geoscience for evaluating microscale properties relevant to depositional environment, diagenesis, and the process of fluid generation, transport, and storage. However, despite thousands of studies which have incorporated SEM methods, the inability of SEM to differentiate sedimentary organic matters types has hampered the pace of scientific advancement. In this study, we show that SEM cathodoluminescence properties can be used to identify and characterize sedimentary organic matter at low terminal maturity conditions 11 varied mudstone samples with a broad array of sedimentary organic matters types, ranging from the Paleoproterozoic to Eocene in each, were investigated. Sedimentary organic matters fluorescence intensity and Cl intensity showed an almost 1-to-1 correspondence, with certain exceptions in true samples potentially related to radiolytic alteration. Therefore, because Cl emission can be used as a proxy for fluorescence emissions from sedimentary organic matter, Cl emission during SEM visualization can be used to differentiate fluorescence from non-fluorescent sedimentary organic matters. This result will allow Cl to be used as a visual means to quickly differentiate sedimentary organic matter types without employing correlative optical microscopy, and could be widely and rapidly adapted for SEM-based studies in geoscience.
Hi, my name is Muhammad Aiman bin Rosli. I want to explain about one of the biggest benefit of electron microscope is that they let us see the unseen. They allow us to view objects at the atomic and molecular level, showing detail far beyond what light microscope can reveal in real-life application. They are used in many fields. In geology and earth science, we use them to study mineral, fossil, and rock composition to understand earth history and resources. In nanotechnology, electron microscope help design very tiny devices like nanorobot or drug delivery system by letting us observe and control atom. For material phasure analysis, we can find out why machine and product break by examining microcrack and structural fault. Finally, they support scientific discovery by giving insight that help develop new theories, better tools, and advanced technology in both research and industry. Okay, we move to the challenge. Even though electron microscope are powerful tools, they come with several challenges. First, there is a high cost involved, both for the instrument and for its ongoing maintenance. Second, they are operationally complex. They are require vacuum system and electromagnetic shielding, and they are sensitive to vibration and electromagnetic noise, which can affect the result. Third, skilled human resources are required. You need trained operator with strong interdisciplinary knowledge to use them properly. Fourth, the sample preparation process can be difficult. It often needs thinning or coating, and it's not suitable for every material. Lastly, the analysis can be time consuming because of the large amount of the data generated. It also requires advanced interpretation tools to make sense of the result. Okay, we move to the future development and innovation. In the future, electron microscope will continue to improve. They will become sharper than ever, giving higher resolution so we can see individual atoms more clearly. With environmental SEM, microscope will work under more natural conditions such as imaging wet or soft sample without damaging them, great for studying biology and food science. Artificial intelligence or AI will help us analyze complex images faster, detect pattern, and reduce human error. There will be multi-tool integration where electron microscopes are combined with tools like AFM or X-ray analysis for better and more complete data. We will also be able to do real-time observation, watching material change under pressure of heat, like observing a battery as it charges. Lastly, microscope will become more accessible with simpler control that allow even students and new users to explore the microscopic world more easily and safely.
Conclusion: the electron microscope. In conclusion, the electron microscope is a powerful tool that helps scientists see very tiny things clearly. It can show things that are too small to see with a normal microscope. In geology, it helps scientists study rock, mineral, and tiny fossils. This gives us more information about the Earth and its history. Even though the electron microscope is expensive and needs special care to use, It is very helpful. It makes scientists better and help us discover many things about the world around us.
This is the link of reference about the information of electron microscope.
That brings us to the end of our presentation. Thank you for your time and attention. We hope the information shared today has been insightful and valuable. If you have any question or you would like to discuss anything further, we'd be happy to connect. Once again, thank you and have a great day ahead.